this is another example where we are going to apply Coulomb's law, and then we are going to apply Newton's gravitational law. You will see here we are dealing with a hydrogen atom. So there's a proton at the center, and we are going to assume that it's stationary. And then there's an electron that moves around in a circular orbit around the proton. The first part is asking to find the electrostatic attraction force between the electron and the proton. In the second part, part B, they are asking to find the gravitational force of attraction between the two masses, that is the electron and the proton. And finally, we need to take the electrostatic force over gravitational force and get that ratio. So first, let's figure out the forces acting between these two particles. So electrostatic forces, you can see there's a negatively charged particle, the electron, that is moving around. The positive charge is at the center, stationary. These are opposite sign charges. As a result, there's going to be attractive forces. So proton is pulling on the electron, and that is in this direction. Similarly, the electron is pulling on the proton, and that force is in this direction. Now you should know that these two forces are equal in magnitude. They are opposite in direction. They are acting on two different objects. They are along the same line. They are of the same kind. As a result, we call these action and reaction pair, action and reaction forces, or a Newton pair. So I'll simply represent the magnitude of this attractive force as Fe. Now we can do the same thing by looking at the gravitational forces acting on this hydrogen atom. If you look at the electron is pulled towards the proton by a force, attractive force, and the proton is again pulled to the electron with the same force, like that. And these are the gravitational attraction forces. So I can call that Fg. I'm just looking at the magnitude of Fg. So these are the forces, and then we have equations to figure out these values. So let's look at that now. So I'll write down those expressions. First, I'll write the magnitude of the electrostatic force, F of E, is given as K, the magnitude of Q1, or that is the proton, magnitude of that charge, and then the magnitude of the charge of the electron, divided by the separation between the two charges. So I'll call that R squared. In a similar way, when we look at the gravitational forces, the magnitude of this gravitational force F of G is given by big G, that is the universal gravitational constant. Hopefully, if you did General Physics 1, you should have done these things. And then the mass of the product of the masses of the two particles. So ME times MP. Now, when it comes to mass, I'm simply putting the magnitudes because we never come across negative masses. However, in charges, you have these positive charges and the negative charges. So you have to take explicitly take the magnitude when we are dealing with charges, because sometimes the charges can be negative. But with mass, in nature, we always see positive mass. We don't see like anti-mass or something like that. So always it's the positive value. And then divided by R squared. You can see this represents the gravitational law stated by Newton. And this is again an inverse square law. You can see 1 over R squared. Similar to Coulomb's law, where again you have this 1 over R squared variation. Now I am going to plug in the numbers. So the first part, part A, we are asked to find the electrostatic attractive force between the electron and the proton. So I am going to simply substitute the values. K is 8.99 times 10 to the power 9. multiplied by the electronic charge of the proton and the electronic charge of the electron, and you can see they are the same magnitude wise. The electronic charge of the proton and the electron are the same. So you should remember that is 1.602 times 10 to the power minus 19 coulombs. Now I'm not going to write down the units for each term, but remember I have to take the square of this because they are of the same value. And then I have to divide this by the separation between the two particles, and that was a nanometer value. So the prefix nano comes into the picture. So 0.053 nanometers. So I'm going to convert that into meters, 10 to the power minus 9. And always remember, in the denominator you have to take the square of this. It's not just the value, you have to take the square of this value. And then you can simplify this. You should get 8.2 times 10 to the power minus 8 newtons as the magnitude of the electrostatic attractive force between the two particles. Now this answer is up to 2 sig figs. Now similarly, for part B, we are looking at the magnitude of the gravitational attractive force between the two particles. So that is Fg. So big G is 6.67 times 10 to the power minus 11. It's a very small value. Multiplied by the mass of the electron, which is 9.11 times 10 to the power minus 31. Remember, those are kilograms. But I'm dropping that. I'm finally going to put the units of SI units of force, because this entire expression simplifies to newtons, or the units of forces. So then here the mass of the proton, 1.67 times 10 to the power minus 27. And then again I have to divide by the separation between the two particles, which is again 0.053 times 10 to the power minus 9 and squared. And then this value, you are going to see that's going to be 3.6 times 10 to the power minus 47 newtons. So you can see, compared with the electrostatic force, the gravitational force that is between the electron and the proton inside the hydrogen atom is extremely small. It's negligible. We don't have sophisticated instruments to actually check or detect such a small variation. So this is the answer for part A, and this is the answer for part B. Part B also asks another question. So that means find the ratio between Fe and Fg. So it's straightforward. You simply divide these two. So 8.2 times 10 to the power minus 8 newtons divided by 3.6 times 10 to the power minus 47 newtons. And then you are going to get a factor, because the newtons cancels out in denominator and the numerator. You will get 2.3 times 10 to the power 39. So that's this factor. So that means, in terms of the forces inside the hydrogen atom, if we consider that the electron is moving in a circular path, then we can conclude that the electrostatic force is order of magnitude 10 to the power 39 times larger than the gravitational force between the electron and the proton. So you can see, this clearly tells you that at these small length scale, the size of electrons, the size of the molecules, atoms, certain materials, the electrostatic force dominates the gravitational force. However, at large length scales, that mean astronomical units, light years, the distance between stars, the size of the Milky Way. So at those length scales, gravitational forces dominates. As you know, there are four types of forces in our universe: electrostatic force, gravitational force, weak nuclear force, strong nuclear force. So these two forces are two of those four forces. And what we say is that at longer length scales, at larger length scales, gravitational force dominates. However, at the small length scale, electrostatic forces dominates. So this is an example to justify that's the situation.